All right, let's dive into something we all see pretty much every day, but I promise you've never seen it like this. We're talking about clouds, and we're going to unpack some really incredible research that's giving us, for the very first time, a true three-dimensional map of all the cloud systems on Earth.
I mean, really think about it. You look up, and what you see is this kind of flat, two-dimensional painting of white and gray across the sky. But that's not what clouds are. They're these massive, complex structures with real height, real depth, all these layers. And it turns out understanding that vertical structure is the absolute key to understanding how they affect our climate. So, what have we been missing this whole time?
So, the first part of this story really starts with a huge challenge. How in the world do you even begin to map something as big and complicated as Earth's clouds in 3D? From space?
You know, for years, our best, most advanced satellites, the ones with LiDAR and radar, they've given us these amazingly detailed profiles of clouds, straight down. But, and this is a big but, the view is incredibly narrow. It's like trying to watch a whole movie by looking through a single drinking straw. You get one perfect little slice, but you're missing almost the entire picture.
So scientists took that one perfect slice. Each one is called a cloud vertical structure, or CVS for short. The best way to think about it is like a single vertical pixel of cloud data. It tells you exactly what's happening in that one spot. Are the clouds high, middle, low, or stacked on top of each other? The real puzzle was, how do you take millions of these tiny individual pixels and build a full global picture out of them?
So, how did they do it? How did they stitch together all those skinny little observations into a map that actually makes sense? Well, the method they came up with is just incredibly clever. It's basically a four-step process. First, they just gather up thousands and thousands of these CVS pixels. Then they take a big area, say 400 kilometers wide, and for a whole month, they just count how often each type of cloud structure shows up. This gives every region on Earth its own unique statistical fingerprint of its typical cloud recipe. And for the final step, they just fed all those fingerprints into a computer and told it to find groups that looked alike. And what came out was something totally new. They call them active cloud regimes, or ACRs. An ACR isn't just one type of cloud. It's a recurring mixture, a common recipe of different cloud structures. Really, the best way to get your head around it is to just think of them as the world's dominant cloud families. Each one has its own unique personality.
So after all that number crunching, the researchers landed on 10 distinct cloud families that basically run the show in our atmosphere. So, let's meet some of them.
And these families, they cover the whole spectrum. We're talking everything from those deep, monstrous storm clouds you find in the tropics, all the way to the wispy, icy clouds way up at the poles. And of course, those huge, bright white blankets of clouds that just sit over the ocean for days.
Okay, so for example, you've got ACR1. That's the tropical deep convection family. Just picture those massive, towering thunderheads. Then, often right nearby, you'll find ACR2, which is made of all the high, icy cirrus clouds and those classic anvil tops that spread out from the big storms. Then, jump over the ocean and you'll find ACR6, marine stratocumulus. Those are the endless, flat-looking sheets of low clouds that act like a giant sun shield for the planet.
And it's not just about the warm spots. ACR7 is the family of big, gloomy storm systems that roll through the higher latitudes. And then you have the complete opposite, ACR10, the arid and mountain family. This is literally the least cloudy group on the whole planet. You find it over deserts like the Sahara or over the massive dry ice sheet of Antarctica. So for the very first time, we have this complete global playbook of cloud systems, all based on their 3D structure.
Okay, so a fancy new cloud catalog is cool and all, but why does this actually matter? Why is a 3D map of cloud families such a big deal? Well, because it takes us right to the heart of one of the biggest questions in climate science. How do clouds control the Earth's temperature?
As the researchers who did this work put it, this new way of looking at things gives us a window into how these different cloud systems are actually managing energy in the atmosphere. It's not just about whether a cloud is bright or dark anymore. It's about its shape, its height, its whole personality.
Let's put two of these cloud families head to head so you can really see what I mean. On one side, we have ACR2, those high, thin, icy cirrus clouds. They're so thin that most sunlight just sails right through them. But because they're way up high and really cold, they're amazing at trapping heat that's trying to escape from the Earth below. They're like a greenhouse blanket. On the other side, you have ACR6, those low, thick, watery clouds. They do the exact opposite. They're like a giant mirror, reflecting a ton of sunlight right back into space before it can even warm us up.
And here's the punchline. The data shows it clear as day. Those high, thin, blanket-like clouds from ACR2, they have a net warming effect on the atmosphere. Meanwhile, the low, thick, mirror-like clouds from ACR6 have a huge net cooling effect. You've got two different cloud structures leading to two totally opposite impacts on the planet's energy, and that is why seeing in 3D is an absolute game changer.
So this brings us to the final piece of the puzzle, and honestly, it might be the most important. Now that we have this real-world map of clouds, we can use it to give our climate models a serious reality check.
For the very first time, we basically have a global answer key for what 3D clouds are supposed to look like. So scientists can take their super complex climate models, look at the clouds they produce, and compare them directly to what we now know is happening in the real world. It's like we can finally grade their homework.
And when they did exactly that with one of NASA's top-tier models, they found some pretty big issues. For starters, the model really struggles to build those deep, stormy cloud systems in the tropics. At the same time, it makes way too many of those high, icy clouds and has them produce way too much rain, which just isn't what happens. And it has a really hard time creating those big, uniform sheets of ocean clouds.
And I'm not talking about a small error. To put a number on it, the model creates 64% fewer of those really critical deep tropical storm systems than we actually see in the real world. That is a massive blind spot. But here is the absolute wildest part of the whole thing. Even with all those mistakes, the model as a whole gets the planet's total energy balance pretty much right. How is that possible? Well, it turns out it's getting the right answer for the completely wrong reasons. Big errors are just happening to cancel each other out. Like not enough rain from this type of cloud is being canceled out by way too much rain from that type of cloud. It's like getting a 100 on a math test, but when the teacher looks, your work is a total mess. This new tool lets us finally see that messy work.
So let's wrap this up. What are the big takeaways here? 1. We finally have a global map of cloud families based on what they actually look like in 3 dimensions. 2. We now know for sure that a cloud's vertical structure, its shape and height, is what decides if it's going to warm us up or cool us down. And 3. This amazing new tool is showing us critical, hidden flaws in the climate models we all rely on.
And that leaves us with one last, very important question to think about. We know clouds are one of the biggest uncertainties in climate science. So if even our best models are getting the fundamental nature of clouds wrong, if they're getting the right answers for the wrong reasons, what does that mean for how much we can trust the fine details of their predictions about the future? Well, thanks to this new 3D view, we're finally on the path to finding out.